Yes, sir. Last time you are explaining third harmonic generation and second harmonic generation via levels. So this is just a way of representation to explain that how these three photons combine to give the third harmonic, or because you are give the how the fundamental again uh, uh, converted again we get at the output also, and you give three different ways to get omega at the output.
Yeah, so it's just,
Yeah.
I mean, we have a classical wave picture and then we have a quantum mechanical picture, right? So, I mean, the classical picture, light is like an electromagnetic wave, and we have, we represent it as a wave with some frequency, right? And in the quantum picture, they are composed of photons, where each photon has this unit of energy, h cross omega, where, right? So, mathematically, what we derived was the classical case, right? And we saw that, okay, we can get nonlinear polarization that, so if we have an input wave at omega, then it can induce a polarization at 3 omega, right? And we'll see that from the wave equation, what a wave at frequency 3 omega, right? So you can just accept that and say, okay, yeah, so there's some wave mixing going on, and waves, like some new frequencies are generated and radiated. But you can also look at it in the quantum picture, right? So what is happening at the level of photons? Only photons at omega, of course, because we have just a wave at frequency omega, right? And at the output, we are getting photons at frequency 3 omega, right? So how does that happen? The only way it can happen is if you want to satisfy energy conservation, is that you somehow you take 3 photons at frequency omega, right, and then convert them to a photon at frequency 3 omega. So that's what we are representing with the level diagram, right? And similarly for other processes also.
Okay, sir. Thank you, sir.
Okay. Yeah. Any other questions?
What is the difference between isotropic medium and medium possessing center of symmetry, center of inversion symmetry?
Yeah. So isotropic means that it looks the same in every direction, right? Which means even if I rotate it, so if I rotate my coordinate axis or equally rotate the material by any angle, doesn't matter, it looks the same, right?
So chi2 will be 0 for isotropic medium also.
So an isotropic material is a special case of a centrosymmetric material, right? So not all centrosymmetric materials are isotropic, but all isotropic materials are of course centrosymmetric, right? So isotropic means that you rotate by any angle, it remains the same. So of course it has to satisfy inversion symmetry also, right? But of course you have materials where which satisfy inversion symmetry, but are not isotropic, right? So for example, you have some, let's say some crystal with some crystal axes, right? So for example, silicon, it will have some crystal structure, right? So it has what is known as a cubic lattice. So you have some periodic arrangement of atoms, right? So of course, atoms are then arranged in certain crystal directions, right? Which means if I rotate the crystal in any arbitrary direction, then it doesn't look the same, right? For example, if I rotate by 45 degree, the crystal won't look the same. But if I rotate by 90 or multiples of 90, it looks the same because the crystal planes are like that, cubic crystal, right? So, and it's all made of the same atom, silicon, right? So, and so if you, for example, do an inversion symmetry, like define some origin and then shift all the atoms, so negate the coordinates of all the atoms, it still looks the same. But it's not isotropic, right? So there's a difference. Isotropic means that, so isotropic, for example, would be like some gas or liquid where you have like on average the same atomic or molecular distribution in any direction, right? Whereas for a crystal, it's not the case, right? If I look in some particular direction, the atomic arrangement is different depending on the structure.
Okay.
So
So we have
Amorphous solids, for example, again would be isotropic because they have some random atomic arrangement, which on average is so like glass is isotropic.
Okay,
But
so
regular solids like crystals, like silicon, carbon, diamond, or something will be isotropic, but they are still centrosymmetric.
okay, sir. Thank you, sir. Sir, I have another question. According to STR, special theory of relativity, nothing is instantaneous. So we have
Yeah.
taken the polarization at the time to be dependent on the electric field at the same time.
Yeah,
So
so that's a good question. So you're right. Of course, nothing is instantaneous. So that's just an approximation, right? Which works well in most cases, and we'll specifically look at what are those conditions where that approximation works well, and what are the time scales involved. We look at finite time response, etc. Also. Yeah.
okay, sir. Thank you.
Yeah. Okay. Any other questions? Okay. So then we'll move on. So at the end of the last class, we started discussing this origin of the optical nonlinearity, right? If we zoom in onto the atomic scale, where does the nonlinearity come from? And we said that we can describe the atom as a classical oscillator. So in the usual case, we describe it as a harmonic oscillator, right? So an harmonic oscillator means that you can describe the atom as if it's sitting in some potential well, which is parabolic, right? So this is some u of x, right, which is some parabolic potential, right? And so some external wave, electromagnetic wave comes in and then pushes. So in the classical picture, we can look at the atom as some electron which is attached to the nucleus with some spring constant, right? And the external electromagnetic wave sort of displaces the electron, so it goes away from the equilibrium position, and then there's a restoring force back towards the origin because of the force from the nucleus, right? So, right. So that's the classical harmonic oscillator model or Stopper-Lorentz model of the atom, right? So this is what if you model the atom like this, then basically you get the linear response, right? And what we are saying is how the nonlinear response comes is when this displacement becomes large, right? So if the electric field, incident electric field is large because the optical field has very high intensity, then this displacement becomes large, and as you increase the displacement, this potential doesn't look parabolic anymore, it starts deviating from parabola. Okay. So for small displacements, the atomic potential is well approximated by a parabola, but for large displacements, it starts deviating from a parabola. Okay. So last time, so for example, if we write the force on the electron, right? So that we said we can write as the restoring force from the atom, this spring force towards the nucleus, plus a damping force. Right, this is due to losses, like, I mean, fundamentally it comes from quantum mechanical losses like spontaneous emission, etc. But in the classical picture, it can be modeled as some friction or damping, right? And then the Lorentz force from the incident electromagnetic field, right? So the total force is, of course, the mass times acceleration, and again I'm writing this tilde over the position variable to show it's like some fast oscillating quantity, right? The restoring force I can write as, right, so minus kx. The damping force is given by some constant gamma times the velocity, right? That's how we incorporate damping. And then the Lorentz force is the charge times the electric field, right? So we discussed last time that we neglect the V cross B term, right? Because for most cases the velocity of the electron here is much lower than the speed of light. So V over C is very small, much smaller than 1. So we can neglect the V cross B term, right? So we just keep the V term. Right, so if you now solve this kind of equation, you will get that the position variable x varies at the same frequency. So this E has some frequency, right? The incident electric field. You will see that the x, the position coordinate, varies at the same frequency as my input frequency, right? It's like a driven simple harmonic oscillator. So the responses are the same frequency as my drive, and that's the linear response, right? In order to get a nonlinear response, what we do is we say that the restoring force is no longer harmonic, right, or linear, but you could have additional terms, right? So the first additional term, of course, I could write would be something which is proportional to x square, right? Right, and so if you have a force which is proportional to x square, then this u, which is the integral of the force times the displacement, right? You would see we'll have a term of x cube, right? So the higher order, next higher order term in the potential would be x cube, and an x cube potential you can see is not, it's not symmetric about the origin, right? So if I add x cube to this x square looking potential, it will start looking something like this. So it will go up on one side and then go down on the other side, right? Because it's not centrosymmetric, right? So that would give rise to chi2, the first term which has force dependent on x square and or equivalently potential dependent on x cube will give you a non-centrosymmetric potential, right? And that will give you chi2. Okay, but if you are considering centrosymmetric materials, then you don't have that component of the force, right? Because a centrosymmetric material by definition means that the potential well is symmetric by about the origin, right? So it's invergent symmetric, which means u of x has to be equal to u of minus x, right? Because the atomic potential basically comes from the arrangement of the atoms, right? So that's for centrosymmetric materials, right? So if that's the case, then the first higher order term that can come here has to be proportional to x to the fourth, right? Because x cube will, as I said, give you a non-centrosymmetric potential, right? So what we can do is in the restoring force, we can add a term which is now proportional to x cube, right? So let's say we add this term. Right, so B is some constant which gives sort of how nonlinear this potential becomes, right? So if I add this nonlinear term to the force, to the restoring force, then the potential from here you can see we'll have x to the 4, right? So the potential here looks like right, so it will look something like this. So for small values of x, the first term dominates. It looks like a parabola. As you start increasing x, this term starts contributing, it starts deviating from that. Okay, and then this b, how the bigger this b is, the more nonlinear the potential, or the more nonlinear the material is, right? So this b is something to do with the strength of the nonlinearity. Right, so then this becomes our equation for the anharmonic oscillator, right? If we include the first higher order term for a center symmetry material. Okay. So then how do we go about solving this? Of course, my input optical wave, let's say, has some certain frequencies present, right? So, since this first nonlinear term gives a third order interaction, right? So we saw that for center symmetric materials, chi2 is 0, chi3 is the first nonlinear term, and this term we'll see will give rise to chi3. So, and in chi3 we saw that the nonlinear polarization is proportional to product, in general, is a product of three electric field terms, right? So in general, let's say that my input wave um, so it's some collection of frequencies, right? So for example, we could consider like n equal to 1, 2, 3, so three different frequencies present, but it could be anything, any number of frequencies, right? And then basically the way to solve this is using perturbation theory. So we recognize the fact that usually this term, the nonlinear term, is much smaller than the linear terms. So we can use perturbation theory to solve it, right? So if you recall perturbation theory, what we do first is we introduce this factor lambda. Okay. So this is some scaling parameter which, let's say, can vary from 0 to 1. Okay. So we say, okay, our input is scaled by this factor lambda, and then we seek solutions, which is a power series in lambda, right? So okay, so we seek solution for the position x as a power series in lambda. So lambda times some x1, that's the first linear term, then plus lambda square times x2 plus lambda cube times x3, so on, right? So the higher order terms are scaled by higher powers of lambda, so they are higher orders in perturbation, right? So hopefully this is somewhat familiar from your, I don't know, like quantum mechanics course or something, or mathematical physics, right? So basically in this equation, we just plug in, so we replace E by lambda E, and then plug in X by this solution, right, as a power series in lambda. So this is some lambda is some perturbation parameter. Right, so it could take some value between 0 and 1, and finally when we solve it, we put lambda equal to 1, right? It's sort of what we do. Okay, so basically, yeah, you plug the solution for x into this equation, right, and then you'll get factors of lambda, lambda square, lambda cube, etc. In this equation, right? And then if this equation has to hold, then basically, so you'll get something like, so when you plug that in, and let's say you take all the terms on one side, you'll get some coefficients times lambda plus some other coefficients times lambda square plus some other coefficients times lambda cube and so on equal to 0, right? And if this has to be valid for any value of lambda, that means these coefficients have to be 0, right? So that's where we, or that's how we solve it. So we collect terms which are the coefficients of some lambda to the n for the nth order perturbation solution. Okay, so we'll have to erase this here. Okay, so if I look at the term which is the coefficient of lambda to the 1, the first linear term, you get this equation.
So that was the restricted area of the board.
Thanks for letting me know. This is here. So the lambda term will give me right. So you can see, so if I plug in x equal to this here, right. So what will be the terms which will have lambda? So in this first case, this is a double derivative, so I'll get x1 double dot, right, with lambda. This is what we get here, right? And then from this term, we'll get omega naught square x1, right? So we just plug in x here, so that's what we get here. And then again from x dot, we'll get x1 dot. It's here, right? Yeah, this is of course just since you put e equal to lambda times e, then this will have a lambda here, so you get the e over m term here. And then the nonlinear term is, right? So we cube this thing, so that there won't be any lambda term from this term, right? So that doesn't show here. Okay, I hope that's clear. Similarly, we can look for the lambda square, coefficient of lambda square. So as you can guess, you get x2 terms now. So x2 double dot. So the second order perturbation right? So we'll get all these terms, the acceleration term, the restoring force, and the damping term with x2, right, for lambda square. But the driving force will not show up because that only has a lambda, right? And we are looking for lambda square, so that won't show up in the second order term. And similarly, this cube term, because we're cubing this whole thing, it won't have a lambda square term, right? Now we can look at the lambda cube term. Now we'll get into the third order perturbation. Okay, so again, I'll get these terms, the acceleration, the restoring force, and the damping terms with x3, right? This won't show up again because this has lambda and we're looking for lambda cube. But now this nonlinear term will give me a lambda cube because when I cube this thing, the first term cubed gives me lambda cube, right? So there I'll get a x1 cubed, which is what is coming. Okay. So basically we have these three equations which give me the first, second, and third order perturbation solutions. Right? So this first, this gives me the linear response of the material or the linear susceptibility. Right? And this will give me the second order response for type 2. And this will give me the third order for type 3. Right, so let's look at the first linear response term. Right, so the electric field we can write as let's say sum of some input frequencies. Right, so this is basically just the harmonic oscillator equation, right, with some driving term. So we know that the solution for that looks like something which goes at the same frequency as my drive. Right, so I can look for solutions. So if I call this, I don't know, equation 1. So for equation 1, you can look for solution. So x1 is the solution for equation 1. You can again just look, seek solutions like this. So the same frequencies which are present in my input, I say that my output, or which is the position in this case, has is a sum of harmonic terms of those frequencies. Okay, so all that's left to find is the values of these coefficients of the amplitudes at the particular frequencies. Right, these are, you can think of it Fourier coefficients. Right? So it's very straightforward, right? You just plug this into this equation and plug ET into this equation, and then equate e to the I omega, the coefficients of e to the I omega nt. Right? So you'll see that x1 at omega n, you can write like this. It's proportional to the electric field at omega n, which we of course expect. And in the denominator you get this term which we define as d of omega n. So this d of omega n is a function right? So d of right. So if I plug in x1 equal to this here, you will see that so first term is a double derivative. So I'll get an omega n square in the front, right? So that's this omega n square here. And then there's an omega naught square which comes from here, right? So omega naught square minus, so omega n square comes from here, omega naught square is already there. And then this second term is a single derivative, so that gives me an omega n, or I times omega n, because it's e to the I omega n. So you get this whole factor in front of x1 omega n, right? So I hope this solution makes sense. Okay, so you can see that, of course, the position, the first order solution of the electronic displacement is proportional to the electric field applied. That's the linear response, right? So, of course, you can see that this x1 gives me a dipole moment, right? So the electronic charge times this displacement will be the dipole moment, and if that's proportional to E, that's the linear response, right? And it's frequency dependent, right? It depends on omega n. If I change omega n, this value changes. And also that it's a complex quantity, right? Which means what? That the displacement is not in phase with my driving field, right? So there's some phase difference between my displacement, which is also oscillating at omega n, and my drive, the electric field, which is also oscillating at omega n, right? If this was a real quantity, then both are in phase. Okay. Right. So from here, straightforward, we can just define from the displacement, we can define a polarization. So the linear polarization, so I call it P1 at frequency omega n. So the dipole moment would be minus of the electronic charge times the displacement, right? That's the atomic dipole moment. And if I multiply by the atomic density, that gives me the dipole moment per unit volume, which is polarization. Okay, right? So this I can write as right. So I got an expression for the linear polarization, which is proportional to the electric field applied, right? And what is the relation between the polarization and the electric field? That's in terms of the susceptibility, right? So the linear susceptibility, if you remember, is basically that, right? So the constant of proportionality here is chi, right, with this factor of epsilon naught. So you can see, I can straight away write chi1, the linear susceptibility, okay. So we got an expression for the linear or the first order susceptibility. Okay. So things to note here, it scales with the atomic density, right? So if you have a denser material, then typically you have a higher susceptibility, right? So, and you know that susceptibility is, for example, is what gives you refractive index. So that's why, for example, solids have higher refractive indices than liquids or gases, right? The other thing is frequency dependent. So this is actually a function of omega, right? I mean, I can even get rid of this n subscript. So just write as chi at a frequency omega is given by that. Right? So it's frequency dependent, which means the susceptibility depends on frequency. It's not a constant. Typically, for example, when we say refractive index of glass is 1.4, right? That's strictly not a very accurate statement. We have to say 1.4 at what frequency or what wavelength, right? Because it actually depends on it. But under certain approximations, we can sort of get rid of this frequency dependence. We'll discuss that. Right, and then the third thing to note is that this d of omega is a complex number. So susceptibilities in general are complex numbers, right? So again, if you recall your basic electrostatics or electromagnetism, we define the permittivity, right, as 1 plus chi, right? So remember, so d is epsilon naught e plus p, and p is epsilon chi e. So this is epsilon naught 1 plus chi e, right, which is. So this is the dielectric constant. Right, so this is the relative permittivity. So ER, which is E by epsilon naught. Right, so the relative permittivity is 1 plus the susceptibility. And I hope you also recall that I can define a refractive index as the square root of the relative permittivity. Okay, so that's 1 plus right. So now if chi1 is a complex number, then this has a real part and imaginary part, right? So the real part gives you the usual refractive index, and the imaginary part gives you absorption, right? So I can write this as some n1 plus I, or usually how it's written is n plus ik, right? So there's a real part and then there's a imaginary part, or sometimes it's written as, this is a better notation, the real plus the imaginary. Right, so you can see that, so this has some functional form. So I can plot the real part of the refractive index and the imaginary part. So this is what, so this is refractive index, right? And this gives me absorption. So the alpha that, so if you recall your Beer-Lambert law of absorption, so the intensity in a medium goes down exponentially, right, with this coefficient alpha. So that alpha is proportional to this imaginary part, right? So we can see how the real and the imaginary part look, right? Because we know the functional form of this D. And so how it looks is right? So I'm plotting it as a function of frequency omega. So you can see that here we have a term omega naught square minus omega square, right? So at omega equal to omega naught, this sort of is a minimum. So this chi becomes a maximum, right? And omega naught is the atomic resonance frequency, right? So typically, if you look at, for example, this alpha, which is the imaginary part of the refractive index, that looks like this. So it peaks at this is alpha, right, which is coming from the imaginary part of chi1. Right? So it peaks at the atomic resonance frequency and then falls off. And then if you look at the real part of the refractive index, that typically goes something like the derivative of this. Okay, so this is the refractive index, which comes from the real part. Okay. So typically, for most applications in optics, you want to use the material in a regime where I don't lose my light to absorption, right? So you want to use materials in the transparent regime, right? So for example, when we use optical fibers made of glass, right, we typically use visible or infrared wavelengths. I mean, we go down up to visible wavelengths, but once you start going down to UV, then the glass starts absorbing. Okay, so basically what that means is this omega naught for glass. So for glass, for example, this so glass starts absorbing in the UV range. So if I define lambda naught, which is 2 pi c over this omega naught. So for glass, it's about 160 nanometer, which is in the UV. Okay, so basically, you want to operate mostly here, right? So you want to operate at frequencies which are much smaller than my resonance frequency, such that my alpha is basically 0. Okay, and in that regime, you can see that this refractive index sort of becomes almost constant. Okay, so for example, if I look, so for glass, for example, typically we operate at wavelengths greater than, let's say, I don't know, 500 nanometer, right? So that's more than 3 times, or this, the omega that we operate is less than omega naught by 3 and lower values, right? So basically what we are saying is this omega is much smaller than omega naught. Okay, and for that, this alpha basically almost goes to 0, and the refractive index almost becomes constant, right? So that's what when we say glass has 1.4, that's in this range. So if you start going towards lower wavelengths, right, you start getting some absorption, so an imaginary part will start showing up, and the refractive index will also start changing appreciably if you start going close to the atomic resonance. So this omega naught was the resonance frequency in this sort of ball spring model of the atom, right? But of course, an atom is not that. Right? In an actual atom, you have some discrete energy levels, right, which the atom can sit in. So in the actual quantum picture, the omega naught corresponds to some transition frequency. Okay. So that omega naught basically corresponds to some transition frequency. So as long as you're operating at frequencies which are much smaller than that, so you don't cause any, the probability of causing any transition is basically negligible, then you are in this range, right? So then you don't absorb. Once your omega starts getting close to omega naught, then there's a probability that you can excite the atom to the. So for solids, for example, you have bands, right? So you have a conduction band, valence band, and then there will be a band gap. So this omega naught will be the band gap, right? So for glass, for example, this comes from the band gap. So if you put the band gap Eg equal to h cross omega naught, right? Eg for glass is about 9 electron volt. From that you get this resonance frequency. Okay. Right. So bottom line, for the linear susceptibility, you want to operate in a regime where you don't have any losses, so you don't have any absorption, and that happens when omega is much smaller than omega naught, or basically you're far away from any band gap or any transition. Right. So your wavelengths are much longer than the resonance. What corresponds to the resonance wavelength. Okay, so that's sort of the linear response. Right, so you can also see that so when omega is much less than omega naught, basically only the first term contributes. Right, so d of omega n, so this and this is much smaller than omega naught. If omega naught square, if omega n is much less than omega, right? So basically, d of omega becomes a purely real number, which is omega naught square, right? And so that the susceptibility here becomes purely real, right? If this is just omega naught square, it's a real number, which means you just have some refractive index, and the imaginary part is 0, so you have absorption is 0. Right? And also you can see it becomes independent of frequency if you can neglect omega n. So now this, if this is omega naught square, then this whole expression is a constant, it doesn't depend on omega anymore. So again, now here the refractive index almost becomes constant. Okay? Right. Any question on the linear response? If not, I will erase everything and move to the nonlinear response. And also one thing to note here is that we've just taken a single resonant frequency, right? But in a real case, like an atom could have like multiple energy levels, right? So multiple resonance frequencies. But basically, what happens is that the resonance frequency which is closest to your drive, that is the dominant one. So let's say you have multiple energy levels here, right? So this is some omega naught 1, let's say this is omega naught 2, this is some omega naught 3, right? So if your drive is at certain frequency omega, the closest frequency to that, right, only that dominates, because you see here the difference shows up, right? So the closest omega naught to your drive is the one which dominates, and we can basically neglect all the others. All right. Right, so we're done with the linear. So let's look at the second term. Second term is very straightforward, right? Again, we can sort of look for solutions like harmonic solutions. So x2 is equal to some x2 omega into the I omega t at different frequencies. But if you plug in here, because the right hand side is 0, you can see that the straightforward solution here is x2 is actually 0. Right? So the second order response vanishes because again we are starting from a centrosymmetric potential, right? And this was the inversion symmetry breaking part, so that solution is 0. Right? And then we can look at the third order term. Right? So here what we do is, so we know the solution for x1. We solved that. Okay, so x1t we wrote as right like that, and then we got a solution for x1 at frequency omega n. So you can plug this solution for x1 into here. Okay. So you can see that x1 q I can write like this with 3 coefficients. Okay, so I have some sum of certain frequencies here, and then when I cube it, I'll get terms like which are the product of 3 terms, right? And the frequency goes as, of course, the sum of the 3 frequencies. Is that clear? Straightforward. Right? And then we know that what are the expressions for these x1 at frequency omega, right? So we know x1 at frequency omega is from our first order solution, right? So we just put omega equal to omega m, omega equal to omega n, and omega equal to omega p here. Okay. So this m is the mass of the electron, not this m. So maybe I put. Just put in the expressions for x1 at the different omegas, so you get product of that, right? So this is what your equation reduces to. Of course, I have the exponential term here also, this term. Right, so now this looks like a harmonic oscillator equation with this as the drive term. Right, so this is just my normal simple harmonic oscillator equation, and on the right hand side I have a drive term now. The drive term has a frequency which is omega n plus omega n plus omega n plus omega p. So again, I can seek solutions of the form right, like this, except here now I have omega n plus omega n plus omega, right? So, for example, if I put x3 right, where omega q is omega m plus omega n plus omega p. Right, again plug this in here, equate the coefficients of e to the I. I mean, I've not been keeping track, so everywhere there's a complex conjugate showing up, right? So, if you want to be totally explicit, you have to keep that complex conjugate everywhere, but I mean, the essence of the idea is conveyed if you just keep the one of the terms. So, right, we plug this in here and then we can get an expression for x3 at omega q, just like we did the first order solution, same thing. So now, what you get is x3 no. Right, so in a sense, what happens is I get another factor of d at omega q, right, from here. So when I plug this in here, you get again omega naught square minus omega q square plus 2i omega q gamma, right? So you get d of gamma q, and the others were already present. So, right, so that's my solution to the third order solution to my displacement, right? So again, now if I have a displacement, I can define a dipole moment and I can define a polarization, right? So I can write the third order polarization at frequency omega q, again like atomic density times charge times the displacement, right? And I can equate this to, in terms of the susceptibility, remember, right? So if you remember the third order nonlinear polarization, we wrote as chi3 times the product of three electric fields, right? And we have an expression for the polarization that we just solved, right, which also contains three electric fields here. So the coefficient will give me chi3, right? So it depends on, of course, the input frequencies, right? So by just plugging this in here and then comparing to this, right? So we get the expression for chi3. That's that. Okay, so chi1 was dependent on frequency, right? So it just depended on the frequency of a particular input field. But chi3 can depend on, so if you have three different input fields at three different frequencies, it can depend on all three of them, right? And it's proportional to, again, the atomic density. It's proportional to this factor B, which was the strength of the nonlinearity, right? So the higher the B, of course, the more nonlinear the material, the larger the chi3. Right? And then you get factors of this function of B at different frequencies in the denominator, right? So again, the thing to note here is, again, nonlinear susceptibilities also in general are complex numbers, right? Because these are complex numbers. And so in the chi3 case, the real part of chi3 gives rise to what is called the intensity dependent refractive index. And other things like third harmonic generation, for example, etc. Right? And the imaginary part gives rise to loss again. And for the chi3 case, it gives rise to what is called two photon absorption. Okay, so in the chi1 case, we saw that the real part gave us refractive index, imaginary part gave us just normal linear absorption. The real part of chi3 gives what is known as an intensity dependent refractive index. So we'll learn more about this later. But basically, what happens is it gives rise to something where basically the refractive index now becomes dependent on the intensity of my field. Okay? And then the imaginary part again gives rise to some kind of absorption or loss, but now it's a two photon absorption. Okay? So in the linear absorption case, basically in the quantum picture, what you can think of is basically the atom is absorbing a photon and going to some higher energy level, right? So if the photon has energy which is higher than the transition here, then it will absorb that photon, right? That gives absorption. In this case, what's happening is it's absorbing two photons at a time. So that's why it's called photon. We'll learn the details about this later, but just to. So there is some terminology here. So usually the real part of the susceptibilities give rise to processes which are known as parametric. Okay, and then imaginary parts of the nonlinear susceptibilities give rise to non-parametric processes. So parametric processes in the nonlinear optics context basically means that, let's say you have multiple optical fields propagating within the medium and interacting using some nonlinear process. Basically, energy is exchanged between the optical fields, whereas the material remains the same. There is no change undergoing, or the material is not undergoing any change at all. There is no exchange of energy between the optical field and the material. Okay? So the material is just acting as some sort of intermediary, and finally everything is happening within the optical fields themselves. So there is no loss of energy from the optical fields. Those are known as parametric processes. And typically the real part of nonlinear susceptibilities give rise to those processes. The imaginary parts give rise to non-parametric processes, where of course you can see there is some kind of loss involved, right? So what is absorption? Basically you are taking energy from the optical field and then dumping it into the medium, right, which is eventually lost as heat or what have you. So those processes which actually exchange energy between the medium and the optical fields are called non-parametric. So some examples are Raman and Brillouin scattering, which we'll discuss towards the end of the course. Okay, so I can also, so you remember that the linear susceptibility had only this one factor of d omega in the denominator, right? It had some n times something divided by m times d. So I can also write the chi3 as a product of the linear susceptibilities at those particular frequencies. Okay, so I can just rewrite it like this. So you can see that the nonlinear susceptibilities can be written as a product of the linear susceptibilities at those individual frequencies. Okay. And again, if you want to operate in a regime where you want to avoid any loss, right? So you want to only have parametric processes. Then again, you have to operate such that your frequencies, so omega n, omega p, and as a result omega q, are all much smaller than your resonance frequency. Okay, which means all the d omegas I can just approximate as omega naught square and neglect the omega dependent terms. Right, so basically I'll replace all these d's as just omega naught square. So you can see I'll just get a real number. Right, so in this regime basically, so basically this is far off resonant operation, right? So again, let's say the material has some resonant frequency omega naught. All my fields omega n, omega m, omega p, etc. are all which are far away from the resonance. Right? Under that condition, I can approximate chi3 as just a number, just a real number, right? So no imaginary part, which means no
Excuse me,
losses.
sir. Excuse me, sir.
Yeah.
Video is not available, sir, now. Only you're
Sorry?
audible. We can hear you, but not able to see the screen board.
I don't know. From my side, everything looks fine, and the video is still streaming.
Yes, sir, I also cannot see.
So
So
most
Nobody.
I also cannot see sir blackboard.
Yes, sir, it's not visible.
Same issue with me, sir.
Can you see now?
Yes, sir.
Yes.
Yes.
Okay. I don't know what happened. I just stopped sharing and started resharing. So okay. Right. So in the far off resonant operation, right? Phi3 is just a number. It depends on just constants, right? Atomic density, epsilon naught, mass of electron, charge of electron, omega naught is the resonant frequency of the material, and this factor B, which was basically how anharmonic the potential was, right? So that is giving you some strength of the nonlinearity. So we can also try to estimate B. Right, so the approximation we can, or yeah, so the approximation that we do is that, let's say, so we know the atom has some sort of size, right? There's some atomic dimension like the Bohr radius or something, right, which gives sort of the size of the atom. And now when I apply my external electromagnetic field, this sort of gets distorted. So let's say if the displacement becomes of the order of the atomic dimension, okay, then the cloud looks really distorted, right?
Sir,
And
again
then
the
we
same
can,
problem.
I don't know what's going on. Because from my side, it's still sharing. I'll do that again. It's fine now?
Yes, sir.
Okay. So we say that when the electronic displacement becomes of the order of the atomic dimension, then the cloud is sort of getting really distorted, and the nonlinear part of the restoring force becomes comparable to the linear part. Okay. So basically, we are saying that so the linear part of the restoring force is this, right? And the nonlinear part of the restoring force was this, right? So we are saying when x becomes d, then these two terms become comparable. So you put x equal to d and equate the two.
Sir, can
You
you
can
just
get.
excuse me, sir?
Sorry.
Sorry, sir. So what you have written in the first line, because that was not visible to us. M of omega not equals to.
So if you remember the linear part of the restoring force, that is just m omega naught square x, right? And then the nonlinear part of the restoring force we wrote as m dx cube, right?
Yes, sir.
So I'm just saying when x becomes of the order of d, where d is the atomic dimension, the Bohr radius, then these two terms are becoming comparable, linear and the nonlinear force. Okay, this is just an approximation we are doing to estimate B, basically. Right. So we are saying that when the displacement becomes of the order of the Bohr radius, then the atomic cloud is getting distorted. So this potential that we were talking about, right? So it starts becoming nonlinear once you get to displacements beyond the atomic dimension. right? So the
So
nonlinear.
again, we can't see the video.
We are not able to see the screen, sir.
It's the same
Yeah,
issue, sir.
yeah, I don't know why this is happening. Okay, back now.
Yeah, back now.
Yeah, so basically I'm saying this potential starts becoming nonlinear once the displacement becomes more than the atomic dimension, right? So the linear force and the nonlinear force are comparable when x is d, right? So from that we can estimate b as basically you can see omega naught square by d square. Right? So if you take some typical values, so omega naught is so some band gap of typical materials, right? So it's a few eV, right? So typically omega naught is about 10 to the 16 in that range. So 8 meters per second, and then d is the Bohr radius. So typical dimension is it's a 3 Angstrom, right? So lattice constant of some solid, right? For example, those are some typical values. Right? So okay, so first what we can do is if you put this value of b into the expression for this chi3 here, right? Then you get chi3 just in terms of fundamental constants. Okay, so now you just have fundamental constants, right? Size of the atom, resonance frequency. So if you put these typical values, you get chi3 to be about 10 to the minus 22 meter square per volt square. Okay, and actually tallies quite well with a lot of materials. I mean, you might think we made a lot of approximations. We started with like a classical model of the atom. We only assume one resonance frequency, right? We basically made approximation after approximation, but if you look at the actual values, so for silica glass, so sort of the most popular optical material, the value is about right, very close. So again, so this all is for far off resonant operation, right? So for when your frequencies are much smaller than the resonance. Which is typically the regime we operate in. Okay, so for another type of glass which is called alumina or sapphire, this value is 3 times. So the order of magnitude is basically, so if you look at diamond, it's off by 1 order of magnitude. It's close enough. Right, so diamond has a slightly larger value because the band gap of glass or alumina is about 9 electron volt. So you can see that omega naught is large, right, which is basically Eg by h cross. Whereas for diamond, the band gap is a bit lower, it's about 5.5 Eg. Okay, which means omega naught is lower and omega naught comes in the denominator here, so chi3 is larger by roughly an order of magnitude. If you look at silicon, you can get really large values. So 10 to the minus 19, so like 3 orders of magnitude higher than glass. And again, that's because Eg is really small, so it's about 1 eV for silicon. Right, so that's, you might think that great, silicon is then a super awesome nonlinear material, right? But remember, this is valid only when your frequency is much lower than the band gap, right? So now if your band gap is already very small, then the range of operation is very restricted, right? So for example, for silicon 1.1 eV corresponds to a resonance wavelength of about, I think 1.1 micron, right? Which means you can operate at wavelengths which are much larger than 1.1. So typically, people use silicon only for wavelengths greater than 1.5 micron or so. So you are restricted to the infrared range, right? Whereas glass, alumina, etc., you can use up to visible wavelengths all the way to the edge of the UV, right? So nothing comes for free, basically, right? So you get a high, you can get a very high value, but that's only for a very restricted wavelength range. Sorry. Okay, and what also happens with silicon is that, so let's say you're operating at 1.5, that's like pretty close to the transition wavelength of 1.1. So this approximation is actually not very good. You actually get an imaginary part also, right? So for example, you can get significant 2-photon absorption. And so nonlinear losses also become important, even though you can get a very large Chi3. Correspondingly, you get also larger nonlinear losses. So that basically finishes our discussion of how we sort of the microscopic picture of how these nonlinear susceptibilities originate, right, from the atomic picture. So any questions regarding that? Okay, so move on to the next topic. Okay, I hope the screen is still visible.
Yes, sir.
Yes, sir.
All right, so in the first class, if you recall, we said that the nonlinear susceptibilities are actually tensors, right? So, for example, Chi3 will have 4 indices. Right? So Chi1 has 2 indices, Chi2 has 3 indices. So Chi-n in general has n plus 1 indices, right? So like each of these ijkl could be one of the cardinal directions, let's say, right? So they are sometimes represented as xyz or 1, 2, 3. So each of these indices could be one out of these 3, right? So in general, of course, there are 3 to the 4, 81 independent elements, right? But due to the spatial symmetry of the material, many of these are either 0 or many of them are equal to each other. So first, let's just look at the example of an isotropic medium. Isotropic medium again means that it looks the same in any direction. So I can rotate it by any angle theta, right, about any axis, it looks the same. So some examples are gases, liquids, glasses or amorphous solids. Okay. So turns out for isotropic materials there are only 3 independent elements. So 1, 1, 2, 2. Okay. I mean, I can write it like this, or sometimes you would see this written as say x, x, y, y. So 1, 2, 3 corresponds to x, y. So basically, for isotropic materials, you have only 3. Like instead of 81 numbers, I only need to specify 3 numbers, and all the other are either 0 or related to these. Okay. So in general, I can write any tensor element okay, where these deltas are the chronicle data function. So delta ij means if I equal to j, then it's 1 or 0 otherwise. Right. So any ij, kl, any tensor element, I can just write in terms of these 3 parameters. So you can see that basically if the first 2 indices are equal, like if the first 2 indices are equal and the last 2 indices are equal, so delta ij, delta kl, then that element is equal to just the chi1 and 2. Right? Which, so from here basically it means that chi 2, 2, 3, 3, or for example chi 1, 1, 3, 3, they are all equal to chi 1, 1, 2. Right? It sort of should make sense. Like all it matters is that. So what does this mean, right? This means that I'm applying a field. So 1, 1, 2, 2 means. So j, k, l corresponds to the directions of the applied fields, and I corresponds to the direction of the induced polarization, right? So it doesn't matter which x, y, z it is, right? As long as 2 of these indices are equal, because it's an isotropic medium, it doesn't matter, right? 2 of them are along one direction, the other one is a 90-degree to it. Doesn't matter which particular direction because it's isotropic, so they are all equal. Right? Similarly, these ones, so chi 2, 3, 2, 3 will be equal to this, or 3, 1, 3, 1. Right? And basically you can derive all these symmetries from the basic property. So if you have an isotropic material, there is no preferred direction, right? So if I apply a bunch of fields, then the total electric field, if it's in some direction, then the polarization induced also has to be in that direction. Right? Because there's no well-defined direction, it looks the same everywhere. So the only way you're defining a direction is by your applied fields. So the net resultant of your applied field, whichever direction that is in, the polarization will also be induced in that direction. Okay. So, sorry?
So will you explain the isotropic concept parenthesis 2233 again? Because I just couldn't understand.
So
That means you said na कि this is isotropic, the two fields are in the same direction, and if other is
yeah, so 1122 means what? Two of the fields are in the y direction, one is in the x direction, and I'm looking at the induced polarization in the x direction. Right? I'm saying that is the same as if I apply two fields in the z direction, one in the y direction, and looking at the induced field in the y direction. Because I mean it's isotropic, right? So this is almost looks like a 90-degree rotation. Is that clear?
okay.
Right, I can rotate my coordinate axes in whatever direction. Right, if the material is isotropic, it doesn't matter.
Okay, sir.
Right, so here what I've done is I've rotated my coordinate axis such that I've replaced, so I've rotated it such that y becomes x, z becomes y. Right? So instead of this element, I get this element. But in terms of the material, I mean, it's the same. So the induced polarization, so another way of looking at it is, I mean, the material is isotropic, I can do whatever to the material, there's no change, right? So I can, I don't know, so you have some x, y, z axes, right? So I rotate this whole thing. So initially, let's say they were pointing in y direction, I rotate it, so now they're pointing in x direction. But physically, what is happening is the same, right? Which means the chi3 elements, the magnitude of polarization induced will be the same for the same magnitude of the electric fields. So the chi3 value is the same. Okay, think about it. I mean, one interesting question to begin with is firstly, for an isotropic material, if I'm saying, for example, that the polarization has to be in the same direction as the applied electric field, then you would think that you have only the diagonal terms, right? So, for example, chi 1, 1, 1, 1. So here you apply a field in the one direction, and then you get a polarization also in the one direction. But even for an isotropic material, you can actually have terms such as this, right, which are not diagonal terms. So you can think about why. Also, you can think about why other terms vanish. So, for example, if I look at chi 3, 1, 2, 2, 2, that's 0. Right. So here I'm applying my input fields only in the two direction, and I'm looking at an induced polarization in the one direction. Basically, that cannot happen for an isotropic material. right? Because there is no, isotropic, everything looks the same. There is no like, I don't know, preferred directions. So the only way you are defining directions in the medium is through applied fields, right? So you can see that, of course, this term, if it was non-zero, will violate this, right? I'm applying E along the two direction and then getting polarization along. So those terms are all zero, where three of them are of one type. So like I3 and 3, 1, 2, 2, all these are also zero. Okay. Basically, with these kind of terms, where two of them are in one direction, you can have the three applied fields such that the total field points in some particular direction, and the polarization is engaged in that direction. Right? But with so these kinds of terms, you can never have this kind of situation. So think more about that. Right? And of course, you can have diagonal terms also. So from here, you can see that if all four indices are equal, then all these three terms contribute, and basically this is equal to 2222 is equal to 3333 is equal to the sum of these three. Okay, so basically for an isotropic medium, you don't need to know all the 81 numbers. You just need 3 numbers, and all the others are related. Then another important class of materials are so the point is like I mean these 1, 2, 3 in an isotropic material are just arbitrary directions, right? We are just picking some 1, 2, 3 and saying those are 1, 2, 3. I could equivalently define my coordinate axis such that instead of 1, 2, 3, I have 3, 1, 2, right? That's just a choice of notation. So that's where all these symmetries are coming from. I'm describing the same physical process, but I can choose whatever axis I want for an isotropic medium. So another important class of materials are called cubic crystals. Examples are silicon, germanium, diamond. So here there are 4 independent elements. So these 3 that we were looking at. Plus now the diagonal term is also independent. It's not. It doesn't depend on these in general. Okay, so you need these 4 independent values, and all the others are just combinations of these or dependent. Right. So in general, I can write a tensor element. Okay, so again, these are the molecular data function, and this delta ijkl is 1 only when all the 4 indices are equal. Right, so basically you can see, yeah, so 90-degree rotation, so the diagonal elements are all equal. Right, which means what 90-degree rotations don't matter. If I rotate by 90, take x to y, z. Because it's a cubic crystal, right? So sort of the atoms are arranged around a cube. 90-degree rotations leave the crystal invariant, right? So and similarly, you can see that the terms with 2 indices are still equal. Right? So basically, it's saying that 90-degree rotations leave the crystal invariant. Shall we do? And then we can exploit one further symmetry to basically reduce the number of independent elements even further. Okay, and that's called so almost all the chi3 nonlinear optics are done with these two kinds of either isotropic or cubic. So if you're not clear, yeah, just at home think more about these symmetries of the material and how those particular chi3 terms will be equal, etc. Right? So if you think about this, visualize the material, you can figure it out. Okay, so one further symmetry is called Kleinman symmetry. And this is for far off resonant operation that we talked about. Typically, right, so all the frequencies present in my interaction are all less than or much far away from the resonant frequency. Basically, so then chi3 first is independent of, it becomes a constant, right? You just neglect the omega terms and just keep the omega naught, so it becomes a constant. Okay, and under this condition, basically what happens is if you permute the indices, so like I, J, K, L becomes the same as I, K, J, L. Like you
Sir,
can
could you write
permute.
a lower?
Sorry. So you can permute the indices in whatever fashion you want. They all are equal. Okay, I can permute these indices in whatever fashion under this approximation of far resonant operation where chi3 becomes independent of frequency. This permutation also holds. So this is called also sometimes called full permutation symmetry. Okay, so basically this comes from the fact that so you have the symmetry of it. So if we take the frequency dependence explicitly, right? So I have something like chi3 ijkl. So my three input frequencies are omega m, omega n, omega p, right? So omega n, omega m, and p are in j, k, l directions, right? And that induces a polarization at omega m plus omega p in the I direction, right? So that's my full expression of chi3. Now, of course, I can write this as KJL. So I'm just interchanging these two fields, right? So I can just write this as omega n, omega p, so omega m. Right. So what I've done is I flipped these two. So what I'm doing is I've applied a field E at frequency omega m along the j direction, and along the k direction I've applied a field at frequency omega n. Right. So either I can write this first and then this, so jk, or I can write this first and then this, so kj, right? It's just notation. I mean, they both describe the same thing, right? So this is equal, obviously, and if you now go to far off resonant operation, that means the frequencies are actually don't matter at all, right? Which means I can, whatever is inside the bracket doesn't matter, right? So I can get rid of this. I can just say, okay, if I permute the indices, the chi3 values. Okay, I hope that's clear. So if you explicitly take the frequency dependence of the susceptibility into account, then of course just permuting the indices means like you also have to permute the frequencies to keep the value same. But under far off resonant operations, these frequencies don't show up at all in my chi3 value, so I can just permute the indices. Okay, so you can see that makes life even easier, right? So for isotropic medium, for example, we saw we had these three independent elements. But under Kleinman symmetry, actually these are equal, right? These are just permutations of each other. So, right? So under Kleinman symmetry for isotropic medium, you actually only need one number, right? So you just need, let's say chi3 1 1 2 2, and then all other values you can get from this, right? So all other where two indices are equal to this, and then the diagonal element will be 3 times this. You can check from that formula that we wrote, right? So we had this times delta ij, delta kl plus this times delta il, delta kj, right? So all of them are equal, so you get 3 times. Okay, so you just basically need just one number. So, for example, for silica, this chi, the diagonal element is this value. Okay, and now for cubic crystals, again you can see that now instead of 4 I need only 2 because these 3 become equal. So I need only one of the diagonal ones and one of the ones with these 2 of them equal. Right, and then I can write any tensor element like this. Okay, so just 2 independent elements, and then any tensor element can be written in terms of this. So, for example, if I look at silicon, the diagonal element is about 2 times 10 to the minus 19, while this off diagonal one is about half that value. Okay. So under most regimes of operation, basically, yeah, if you have an isotropic medium, you just need one number. If you have a cubic material, then you just need those 2 numbers, and then you can define the whole chi3 tensor. So 99% of the third order nonlinear optics done can be classified under this regime of operation. I guess, yeah, we'll stop here. Any questions?
Sir, under Kleiman symmetry, the indices can be interchanged and the chi3 remains the same. So
Yeah.
why do we need two chi3s in cubic crystals? Why can't we do it with...
No, so basically in cubic crystals, the diagonal one, well, all 4 indices are the same, is sort of independent of the off diagonal one. Right? So in isotropic material, basically the diagonal one also is just dependent on the diagonal one is 3 times the off diagonal one, right? But in cubic crystal, like depending on the material, it's sort of independent. You cannot compute the diagonal one just from the off diagonal one, or vice versa, right? So in general, they are still independent quantities because the material has a definite structure, right?
Okay, sir. Thank you.
So yeah, that's why so there are 2 independent. So one like a one diagonal value and one off diagonal value. But in an isotropic medium, because you have a further symmetry that is isotropic, which means it looks the same in every direction. It also relates the diagonal and off diagonal. Right, again, so for isotropic, you have this constraint of that the polarization induced has to be in the direction of the net electric field that has been applied to the medium. But for cubic crystal, that's not the case, right? Because you have atoms arranged in some lattice, right? So there are bonds between the atoms in different directions. So it could be that you apply a field in one direction, but the polarization induced is actually in an orthogonal direction, right? So that could be a component of the polarization in the orthogonal direction. Yeah. So of course there is whole big class of materials, right, with many different kinds of crystal structures, and depending on the crystal structures, they would have symmetries where certain. So if you have more complicated crystal structures, then you would need more elements, right? So instead of cubic, if you had some other, like, I don't know, orthorhombic or some other thing, then you would need more. There will be more independent elements. So out of the 81, you need more. Yeah. So if as the crystal has more and more symmetries, the number of elements required is less, right? So isotropic is sort of the perfect symmetry. It looks the same in any direction. So that's sort of, it requires the least. It just requires one value. And then sort of the next most symmetric thing you can think of is a cubic crystal. So any 90-degree rotation in any direction leaves the crystal invariant. So there you require 2.